Alright, so in the last video we talked about how we can have a vector being a displacement vector where it goes from some point A to point B, but it can represent anything with magnitude and direction. So let's do, in this example, let's use velocity. So vector A could still be labeled as A, it could be labeled as V if you wanted. Let's go ahead and label V. Alright, put a vector sign over for good measure. And what are we going to do with this? Well, we need to be able to break stuff into components. There's a good example. So let's say something is actually in a parabolic trajectory like that. Maybe getting a football getting kicked or something. Sorry, I gotta draw some stuff on there. Okay, in this parabolic trajectory, which we're going to learn about in the next chapter, we will see that the velocity, let me get a different color. If I draw the velocity vector at each spot, it actually is changing. So it is changing in magnitude, but it is also changing in direction. Either one of those constitute what's called an acceleration. So if we have a velocity and there's a change in the velocity vector, then some acceleration had to have taken place. And that could be like this, it'd be gravity pointing down the whole time. So the same 9.8 meters per second squared is pulling us down through the whole entire path. Alright, we need to be able to break up this right here, its initial velocity. We call it V naught, and V naught is interchangeable with V initial, it's interchangeable with V1, whatever you want to call the beginning point. Typically one of those two. We need to take this vector, I'll redraw vector V naught. Let's go ahead and create some sort of origin system. This would be in our x direction and our y direction. We need to be able to break this vector up into what's called components. We need an x component and we need a y component. And anytime we have a vector, this is the first step. We've got to do it. If we have forces, accelerations, velocities, displacements, to add them together like we did earlier, unless you have a protractor and a ruler, you are going to have to break them into components first. And there could be z components also. I'm not going to see many z components in this class. Okay, so when we're given a projectile problem like this, they will give us the speed at which it's kicked, so the magnitude of V naught, and they'll also give us this angle. It's the angle from the x-axis. Okay, when they do that, that would be this angle, theta. The whole goal is to break up the vector into a horizontal and a vertical component. So we'll call this V in the x direction and V in the y direction. So no z component needed in this case. And to do so, I'm not ashamed. I literally use SOHCAHTOA still, right? Maybe one of the most valuable acronyms in my life, and I'm not an acronym person at all, but I still write this at the top of tests. Well, I haven't had a test for a while, but I never didn't not use it. If I wanted to find this x component, and we know that angle theta, then and we know the magnitude right here, we would just take the magnitude and multiply it by the cosine of that angle. This is a definition that y'all need to know how to get to. So we're given v naught, the magnitude, and that's the speed, and we're given the angle from the x-axis. Might not be from the x-axis, so you have to make sense of that and make sure you're still getting the x component and the y component. Sakatoa will do that for you. Just don't be afraid to go back to your roots. What about this y component right here? If I want to find the y component, it's going to be equal to that magnitude that it is kicked at. And in this case, if it was a ball that got kicked, times the sine of the angle from the x-axis. So we'll have to do this for every vector. And velocity is one thing, but we'll see it's really important with forces. We're going to start looking at maybe a block or something. It'll have some mass. There's going to be all kinds of forces. Some force P pulling this way, some friction down here maybe. It's going to have some weight, mass times gravity going down. It's going to have a normal force like this. It could be on an angle. Who knows? We have to break up all of these into x and y components. These ones are already in x component and that's already in y component, but we had to break up this one to be able to add them all together. So what does that mean? That means when we add vectors, we add components first. Okay, so for example, and let's go ahead and define how we should write a vector. We will say some vector A has some quantity in the x direction, and we'll put a I. I corresponds to the vector direction in the I direction. So it has a unit length of 1, and I'll go more over this in detail. And then we also have some component in the y direction, and we'll put a j. So the little, it's called the I hat and a j hat. It defines a unit vector in the I direction, which is the x direction. And the unit j direction, which is our y direction. Okay, so to add vectors, let's say I have some vector, let's change it from A, let's say I have some vector B, and this could be a displacement vector. For this example, let's make it just distances, displacement vectors, and we'll be adding them. B is given to us as maybe 2 meters in the I direction, and let's say 5 meters in the j direction. This could also be written as 2I plus 5 meters, 5k, all with meters like that. This is probably more common. Either way is perfectly fine though. If that's vector B and we're given some other vector C and I want to add them, let's say C is equal to 3I, and let's say it's minus 4 in the k direction. B plus A, we need to break up and add them into components. So this is why if we had a vector given to us where the magnitude was given and the direction, we would want to break it up into its x and y coordinates first. We want to put it in I and jk first. I, jk form first. So a plus b, I would take the 2 and the 3. So 2 plus 3, and that's going to be in the I direction. And then I take the 5 and the negative 4. And that's all going to be in the k direction. So adding b plus a gives me 5i plus just 1 in the k direction. And you don't forget the units. This would be in meters. So if I added two vectors together and they had x and y components only, this is how we would do it. How would I subtract them? Well, same thing, except it would be a 2 minus 3 plus a 5 minus a minus 4, all in meters. And this would be in the k direction. Okay, so let's use this one. We added two vectors together and got some new resultant vector that was 5i plus 1k, and the whole thing was in meters. If I wanted to graph that from some origin point, it would literally be 1, 2, 3, 4, 5, and then 1 up. That is what adding the two vectors gave us. We get a displacement of such. And what if I wanted to know how long this was? If I wanted to figure out this length or the magnitude of r, well, we know the y component and we know the x component. So let's just use Pythagorean theorem. 5 squared plus 1 squared. So if you ever need to know the magnitude, it will be the x component squared plus the y component squared. What about if we wanted to know this angle theta right there? We're going to find theta by taking a tangent inverse of the opposite. Remember, TOA? So it'd be the tangent inverse of the opposite over the adjacent. In this case, the y component over the x component. Alright, these are very important. Don't worry, we're going to practice the crap out of those. I'll be damned if you don't know how to break up a vector into components by the time you leave this class. Just know that this vector and all these vector rules apply to anything that can be put into vector notation. So I used displacement and velocity. We could also be talking about accelerations or forces or momentum. The list is pretty heavy. Lots of things have a magnitude and a direction. Alright, we'll talk more about vectors in a little bit.